you will see how we can handle scalability challenge in deep learning and significantly accelerate large-scale training of deep res nets on ImageNet and training deep generative adversarial networks without sacrificing accuracy. You'll also see how we can handle robustness issue with respect to both natural distribution shifts and also adversarial attacks when we are dealing with powerful and informed adversaries. I should acknowledge the great work of my collaborators that are listed here alphabetically. Okay, so deep learning is characterized by massive data sets and also inductive bias from large scale and complex deep neural networks. So to train these deep networks with non-convex loss landscape, the first order methods such as stochastic gradient descent and variance are very popular. But then we want to train these models on multi-GPU systems to improve the speed of training and also scale the compute. Okay, so we know that the size of neural networks grow exponentially. For instance, here we show the number of parameters in millions for some of those recent deep language models. It's not actually super update because, for instance, ChatGPT and GPT-4 will have probably many more number of parameters, but the main message is that we're getting bigger and bigger machine learning models. And this is not only for language models. Here we show the number of parameters and the scale of the model across various modalities, computer vision tasks, language tasks, and also multimodal tasks. As you can see, the number of parameters across different modalities is continuously increasing. So in deep learning, we have large scale deep models. And at the same time, we have a lot of data to learn. You can see the data volume in zettabytes. That's again constantly increasing. So the amount of available data for learning is constantly increasing. So one of the main challenges in deep learning is how to handle scalability when we have massive data sets and also deep models. So what's this data coming from? We can think of Internet of Things, such as smart cities, smart homes, smart wearable devices, and billions of sensors and actuators that are deployed in IoT world. We can think of healthcare domains, such as patient records, medical images, and genomic data. We can think of web content, such as search engines and data centers of big companies like Google, Microsoft, Amazon, and Facebook. We can also think of financial services, such as banks and insurance companies. So practitioners observed that by making models bigger and feeding them more data, we can achieve better performance in terms of learning. But what is the issue then? Is the computation time is the main performance bottleneck, which is due to both the amount of data and also computation time needed to train a model. Basically, training the model is hard because we have large models, and also the amount of data. You can think of both the number of samples we have in our training set and also the dimensionality of the data. So in this context, one critical problem in deep learning is to design learning algorithms that are highly scalable. Okay. So the goal of my research is to design new learning algorithms to reduce computation or training time when we train a deep neural network over multiple GPUs or clients without compromising test error, which is basically our learning goal. Here, GPUs, you can think of in a data center setting when you have a huge data set, which is partitioned among multiple GPUs, and you want to train your favorite model. Or you can think of clients in federated learning settings. For instance, multiple hospitals want to train a model collaboratively, or thousands or millions of phones, they want to train a model together. In addition to performance measures, such as training time and test error, privacy is also critical. to sensitive applications. So ideally, we look for algorithms that they are somehow privacy preserving, because preserving privacy is also an integral part of responsible ethical AI. Also, in real-world settings, it's highly desirable to make sure that our algorithm ensures some level of robustness. So we can think of robustness to natural distribution shifts and also adversarial attacks. That I will elaborate on these points later on. All right, so how we handle a scalability challenge. For image classification tasks, because this is one of the main areas that visual intelligence is interested, we propose non-uniformly quantized stochastic gradient descent, which is a class of gradient compression schemes. And at the time, our methods provide the highest communication compression on the regular hyperparameters that are tuned for the full precision baselines. We also propose two adaptive gradient compression schemes where multiple GPUs or processors estimate distribution of gradients, and adaptively over the course of training, they updates the compression scheme. And we can save at least 60 hours from 95 hours of training deep ResNets on ImageNet without sacrificing test error. Very recently in an ICLR work, we went beyond image classification tasks, and we consider large-scale variational inequality problems. I know it's a bit technical. I will elaborate on this later, but just as an overview, we proposed a quantized generalized extra gradient family of algorithms. And we showed that basically these family of algorithms provide optimal rate of convergence, and we noticeable speedups when training generative adversarial networks, or GANs, on multiple GPUs. Okay. So in the beginning of the talk, I will focus on image classification tasks and basically scalability in image classification and how we can accelerate. And then I move to training large-scale GANs, and later I will go and cover basically the robustness issue. So this is our model. We have a large data set which is partitioned among K processors or GPUs. You can imagine, again, these could be multiple GPUs in a data center setting, or they can be, say, multiple hospitals wants to train a large and deep neural networks together. For instance, one hospital in Tromsø wants to train a model with another hospital in Oslo, maybe collaboratively with hospitals in Japan or, say, South Africa, for instance. So each processor here computes its own stochastic gradient using its own local data, and then processors share and aggregate the stochastic gradients to compute updated parameters. Note that our algorithms can be used in federated learning settings when we train a deep models on data distributed among multiple data owners without exposing the data. Okay. So by increasing the number of processors, the computation cost per processor reduces significantly. However, communication cost to share and synchronize huge gradient vectors increases drastically. And the communication cost may thwart the benefits of the reduction of computation costs. Indeed, communication cost is the main performance bottleneck, and reducing communication cost is a significant problem for data parallel SGD in practice. I will quote this sentence from this well-known survey, Advances and Open Problems in Federated Learning, which says, privacy and communication efficiency are always first-order concerns in federated learning. Okay, how people tackle this communication efficiency problem and how they manage communication costs in multi-GPU and large-scale training. One way is to reduce the frequency of communication, for instance, by local SGD types methods. Basically, it means that instead of updating the server or other GPUs or clients at every single iteration, each processor updates the model locally for multiple iterations or multiple epochs, and then they update the the peers, the other processors, with the model updates or the final model. The other way is to reduce the dimensionality of problem, because we have a very deep neural network, so we can probably prune, sparsify, or quantize the underlying neural network. But we are specifically interested in quantization and sparsification of the stochastic gradients, and in particular, unbiased quantization schemes. Why? Because these schemes enjoy strong theoretical guarantees that hold for a number of problems, like convex, non-convex, smooth, non-smooth, with or without acceleration, and arbitrary data sets or models. We can achieve full precision accuracy using much less memory, and with writing good CUDA kernels, they can be implemented very, very efficiently. And most importantly, these methods provide communication efficiency on the fly. It means that you can still use the same hyperparameters that are tuned for the full precision baseline for your model, like that you use with PyTorch, without any compression, and you achieve speed up. So they are kind of painless for practitioners. Any questions so far? Please feel free to interrupt me in case you have any questions. So, okay. So here we consider our problem. We have a function f, which is, say, an unknown function, but differentiable, maybe smooth. So we don't have access maybe to the function itself, but we can make queries and we get some first order information like gradient or stochastic gradient information. And we want to minimize this function over a huge parameter vector W, where D is the number of parameters. For instance, this W represents all the weights and biases of our deep neural network, and F represents the empirical risk or maybe the true risk in an online setting. So to minimize this function, the basic first order method is gradient descent with update rule as here, and alpha is the step size, but this is not scalable because computing the true gradient is very costly when we have a deep model and huge data set. So instead, we have access to stochastic gradients of f. So we have access to the output of a random function g, such that in expectation, we still get the full batch gradient at any parameter within our space. Okay, in terms of the system model, we consider a synchronous and distributed system with k processors, where each processor computes its own stochastic gradients, and then processors share and aggregate stochastic gradients from all peers to update the model all together in a synchronous fashion. So to reduce the communication costs and accelerate training, Alistar and his colleagues proposed an interesting scheme which produces an unbiased and compressed stochastic gradients very useful for SGD. In their scheme, we have a high dimensional stochastic gradient, for instance, the gradient at some iterations of your favorite model on your favorite data set. And then every coordinate is normalized by the Euclidean norm of the gradient. So imagine you take the sign off and then normalize every coordinate. So you get something between 0 and 1, like this blue point. And then every coordinate is stochastically quantized to one of a small number of levels that are distributed uniformly in the unit interval. So like they consider quantization levels that are uniform between 0 and 1. And their method is called QSGD. So they observed that many of these normalized coordinates are quantized to 0 in expectation. So by basically efficiently encoding those zeros, they can achieve substantial communication savings. But what is the cost of their method is greatly increase the variance, which reduces the speed of convergence. Okay. So stochastic gradients in deep learning are observed to be dense vectors. So it is very unlikely to observe large values of normalized coordinates. Our idea is to use fine intervals for a smaller normalized coordinate to reduce quantization error and control the variance. For instance, suppose that this is the uncompressed, the original normalized coordinate, which is between 1/4 and 1/8. It can be quantized to 1/4 or 1/8, and we set the probabilities within these random quantizations such that in expectation, we still get this blue point. So after the compression operator, we still get some sort of a stochastic gradient, maybe with a little bit additional noise, but still is unbiased. So we recover the actual full precision test error. In the beginning, we focus on this special case of exponentially spaced levels with multiplier 0.5 as the quantization levels, but later on we generalize it to arbitrary levels between 0 and 1, and we establish a trade-off between communication efficiency and convergence speed. It means that if you use more levels of quantization, so you communicate more bits, but then the variance will be smaller, the additional noise is smaller, so you converge faster. Let's see how non-uniform quantization performs with respect to the full precision baseline in terms of scalability. Here we train ResNet 50 on ImageNet, and we show time per epoch for 2, 4, 8 GPUs. And we compare non-uniform quantization with full precision baseline. This is the basically multi-GPU SGD optimizer that people use with a PyTorch without any compression or quantization. So as you can see, the full precision baseline has a negative scalability behavior. And by the way, I should specify each time bar is split into computation time, which is this bottom part, encoding, the middle part, and communication or transmission time, which is the top part. So for full precision SGD, if you increase the number of GPUs, the computation time reduces, but the communication cost dominates the total time per epoch and increases drastically. But we achieve significant scalability improvement. And the encoded non-uniform quantization is basically means that we add additional information theoretically optimal Huffman coding on top of quantization to further reduce communication costs. But these methods, such as uniform quantization and non-uniform quantization, they are kind of heuristic and fixed over the course of training. Like we design some levels between 0 and 1. But empirically, we observe that distribution of gradients actually changes over time, over the course of training. So a quantization method that is optimal at the first iteration won't be optimal even after a single epoch. So there is no fixed method that is optimal throughout the entire training. So here we show like the mean variance of these normalized coordinates when we train ResNet 8, for instance, on CFAR10. You see that the statistics of these stochastic gradients changes over the course of training. For instance, here gradient variance changes very rapidly during the first epoch, but then the next noticeable changes will be after learning or step size decays. So the statistics change, but we can somehow capture, like the changes basically, and we try to estimate the distribution of the gradient, and we optimize our compression scheme based on the statistics of stochastic gradients to achieve the best or optimal compression schemes. Okay. We have a theorem that says basically the speed of training is directly related to the variance of quantization. And this is very intuitive because you can imagine like the compression operator takes a stochastic gradient as input and outputs another kind of a stochastic gradient with additional noise. So if you can control that noise while you reduce communication costs, you can converge much faster because you have a better quality kind of stochastic gradient. Okay, so the idea is to adapt the levels, minimize the variance of quantization with fixed communication budget. So here, V is our stochastic gradients, uncompressed original stochastic gradients. upper sub L outputs the compressed version or quantized version of this. And it has also this H, which captures randomness of quantization, because if you remember, our quantization schemes wants to be unbiased, so it's a random scheme. And then we want to design these S levels between 0 and 1 to minimize this variance as much as possible with fixed communication budget. It means that for every coordinate, we transmit limited number of bits and it's fixed, but then we want to design the best levels. Okay. But unfortunately, minimizing the quantization variance is notoriously hard, non-convex problem. But luckily, we found that optimizing a single level given other levels can be solved efficiently, actually in closed form. So we proposed adapting levels one at a time, or adaptive level quantization, ALQ algorithm, that first it initialized some random levels between 0 and 1, and then it fixed, for instance, all levels and adjust level 1. Again, we have a closed form efficient solution for this, and then we fixed all levels and we adjust L2, and we repeat it until convergence. You note that this method basically converges in less than 50 iterations, so it's very, very efficient. In terms of theory, for general adaptive quantized stochastic gradient descent, and for arbitrary levels between 0 and 1 under general normalization, we establish an upper bound on the variance of quantization and expected number of communication bits. So basically, we know that if we run this method, how many bits at most, basically, each GPU will transmit over the course of training. And we have a control on the additional noise because of the compression. So we can guarantee some convergence rates. That holds for a number of problems. And in terms of variance of quantization, we can show that our upper bounds basically match the lower bounds. So they are tight in the dimensionality of the problem. In terms of convergence, we noted that a naive adoption of available convergence guarantees in the literature results in worst case variance bound over the course of training. But with these adaptive methods, we update the compression scheme over the course of training. So we note that an average variance bound can be applied on a number of problems instead of the worst case bound. So let's see how these methods perform in practice. Here we compare adaptive level quantization to different baseline. Super SGD is the full precision multi-GPU SGD. Again, is the multi-GPU SGD optimizer that people use with their PyTorch without any quantization, without any compression. QSGD-inf is basically the uniform quantization under L-infinity normalization. TRN is ternary quantization under L-infinity normalization. And NUQSGD is basically the non-uniform quantization scheme that I mentioned in the beginning of the talk, which basically sets the levels as exponentially spaced levels with multiplier 0.5 under L2 normalization. So these are our baselines, and all these methods share two quantization hyperparameters. The number of bits is log 2 of the number of quantization levels, which basically explains how much communication budget we have. And the bucket size is a trick in high dimensional normalized compression, where we encode a high dimensional vector in buckets such that each coordinate is normalized by the norm of its corresponding bucket instead of the entire vector. So if you have a huge stochastic gradient, we split it into buckets and we compress each bucket separately. Okay, here we show validation loss when we train ResNet 18 on ImageNet using 4 GPUs. And so the lower is better. Here, Super SGD is this blue line. So Super SGD provides a lower bound on all compression methods. There is no compression with it, but we want to get as close as possible to this lower bound. So you can see that our adaptive methods perform much better the non-adaptive methods in terms of variance of compression. So over the course of training, we get closer and closer. Basically, we are much closer to the full precision SGD. In addition to adaptive level quantization, we also propose another adaptive method, adaptive multiplier quantization, or AMQ. This method models quantization levels as exponentially spaced levels, but then instead of a fixed multiplier 0.5, such as those that baseline non-uniform quantization, it optimizes the multiplier using gradient descent. So AMQ can be considered as an adaptive variant of non-uniform QSGD. Okay, this slide shows the final validation accuracy when we train deep models with 4 GPUs. We train ResNet 110 on CIFAR10 and ResNet 18 on ImageNet. Interestingly, we noticed that using only 3 bits per coordinate, again, instead of full precision, 32 bits, for instance, float for every coordinate of a stochastic gradient, we use 3 bits. So we can match the performance of super SGD with the same optimization hyperparameters on CIFAR10, and we close the gap on ImageNet. And there is at least 1.4% gap between our best performing adaptive methods compared to the previous work. And this way we can save at least 60 hours from 95 hours of training resonance on ImageNet also without sacrificing accuracy. And this was a significant improvement over the state of the art because it was 4 bits non-adaptive methods, the previous SOTA. So we pushed to 3 bits using adaptive quantization. If you remember, I mentioned that these methods share 2 hyperparameters like quantization hyperparameters that are bucket size and the number of bits. Here we want to see the impact of those hyperparameters on different methods. On the left-hand side, we fix the number of bits and we vary the bucket size. And on the right-hand side, we fix the bucket size and we vary the number of bits. You note that, for instance, these non-adaptive methods are very sensitive to the choice of, for instance, bucket size. But our adaptive methods are very robust and always the best across all values of hyperparameters. Why is that? Because regardless of the communication budget or the number of bits per coordinates that we have, and regardless of the normalization, for instance, L2 normalization or L infinity normalization or L1 normalization, or the bucket size, the adaptive compression schemes, they estimate the distribution of a stochastic gradient, and the levels are optimized to match the distribution, to minimize the variance. So it doesn't matter what bucket size or so we select. Okay. So far, I discussed how to accelerate image classification tasks. Now, we go beyond image classification and consider scalability for large-scale monotone variational inequality problems. So monotone variational inequality problems, basically these VI problems shown here, we have a monotone operator like A. You can imagine like it's like a gradient operator for a convex function in a simple case. So our goal is to find this optimal point x star, which this inequality holds. And this is a VI problem that we focus. And we want to accelerate large scale VI problems. It is shown that several important problems can be casted as VI problems, such as convex optimization, saddle points, and general games, with important applications such as training generative adversarial networks, multi-agent robust reinforcement learning, adversarial robust learning, and also auction theory. Okay, so when we have an oracle, and the oracle is called at some point x, within the space of parameters. By the way, we changed a little bit the notation here. So X here is basically represents the parameters, like the weights and biases of the neural networks. So when we call the oracle, the output will be a stochastic dual vector, which is the basically operator at point X plus some measurement error or noise U. And this measurement error or noise, we have two well-known models for the noise in the optimization literature. The absolute noise means that there exists sigma square such that the expected squared norm of the noise is bounded for all parameters. And we have a relative noise, which means that there exists some C such that the expected norm of the noise is bounded by the norm of the operator itself. So when we are closer to the optimal in the relative noise model, the noise will be also smaller. So we expect faster rate of convergence. So here we have, again, a system with K processors, GPU or clients, that they have access to independent and private stochastic dual vectors. We proposed quantized generalized extra gradient family of algorithms, or QGenX. So why it's called extra gradient? Because if you have parameters at iteration t like xt, to move to xt plus 1, basically you have basically two updates, or you need two kind of stochastic dual vectors at every iteration. And these, we had k and 0, we had k and 1, so forth, and we had k half, we had k 1 and half, and so forth. They are sequences of stochastic dual vectors computed and quantized by processor K. Okay. And why it's kind of family of algorithms or generalized family of algorithm? Because by setting different choices of v hat k and t and v hat k t plus half, like here, we can come up with communication efficient and distributed variants of several well-known optimization algorithms that are proposed to solve VI problems. For instance, distributed stochastic dual averaging, distributed and communication efficient stochastic dual extrapolation, and distributed stochastic optimistic dual averaging. All these well-known methods, they were proposed for single GPU, and they basically don't handle the scalability challenge like communication costs, as I mentioned before. But these QGenX basically makes an umbrella that includes all the communication efficient variants of these well-known methods for VI problems. In terms of convergence, we can show that QGenX achieves optimal rate of convergence under both relative noise and absolute noise models. For instance, under relative noise, if we execute QGenX for t iterations on k processors with an adaptive step size of this form and adaptive quantization, then QGenX achieves a fast rate of convergence in the order of 1 over kt. In terms of communication, we also basically established an upper bound on the expected number of communication bits per iteration. Under absolute noise and the same adaptive step size form, again, we achieve an order optimal rate of 1 over a square root of k times t with bounded expected number of communication bits per iteration. So what is the message of this slide? Is like the adaptive step size rule is the same without prior knowledge on the noise profile. And here we show that by increasing the number of processors, we can accelerate convergence for larger scale VI solvers. Here we show QGenX to train Wasserstein-GAN with gradient penalty on CFAR10 and only 3 GPUs. Left-hand side, we show fresh inception distance, which is the standard GAN quality measure. And the right-hand side, we show fine-grained timing results. You can think about this total training time. It turns out that even with the basic compression scheme, and even for a very, very small scale problem, we can still achieve 8% speed up using unbiased quantization. And this speed up does not drastically change the performance. So the FID numbers basically remain almost the same. Okay. Any question regarding the scalability part? Because I'm moving to the robustness and security. So far, so good. Okay. So deep learning models are vulnerable to adversarial examples at the test time. And these are natural or human-crafted modifications to trick neural networks in various, for instance, computer vision tasks. You can see on the left-hand side, with some triggers, the stop sign is classified as 45 meter/hour sign. On the right-hand side, the neural network classifies turtle as rifle with high confidence. But instead of adversarial examples at the training time, we focus on malicious or adversarial agents at the training time instead of the test time. And so basically here we might have an adversarial agent who compromise some of these clients in the distributed setting. And they may target some examples or classes that are underrepresented at the training or validation time using some backdoor or edge case attacks. They can be done through data poisoning or model poisoning, but we are mainly focusing on model availability attacks or Byzantine attacks. And in particular, we consider tailored training time attacks that I will elaborate on this shortly. But tailored training time attacks, it means that the goal of the attacker is to make sure the model is ineffective and useless for all clients, for all users. And the informed attacker has prior knowledge on the aggregation rule that the server wants to apply. So it can provably corrupt the training process, or it can control the optimization trajectory. So in this system, we have multiple honest or good clients or nodes or GPUs that they compute and share through a stochastic gradients. But unfortunately, we have also some compromised clients by the adversary that they communicate arbitrary messages. Those arbitrary messages could be either attacks, or they might be just incorrect updates due to network hardware failure or power outages or so. But we focus on adversarial attacks. In the literature, several robust methods have been proposed based on robust statistic aggregation rules. Essentially, those robust statistic methods are based on using median, like coordinate-wise median or geometric median, instead of averaging. Because if you use median, you will be somehow robust to outliers, intuitively, right? But it turns out that those robust methods are still vulnerable to informed and tailored attacks. So if the attacker knows what you're going to do at the server side, it still can design a successful attack, because the stochastic gradients are noisy. So the attacker can use this noise to design tailored attacks. Okay, what's the meaning of tailored attack? Imagine you have all good clients and they want to minimize an objective function, and without any attack, the direction of updating model parameters is G, but the adversary controls F clients out of total of N clients. So the adversary designs these updates out of total of n updates, but the goal of adversary is to push the model towards the inverse of the good direction or honest direction without any attack. So if the adversary knows the aggregation rule at the server side, it can solve this optimization problem and push the model to an ineffective model. Basically, if you want to minimize an objective, the attacker tries to push you towards maximizing that objective. So the model will be useless for all users and all classes, basically. So our idea is very simple. We propose randomization to confuse the attacker. Instead of one robust aggregation rule, the server collects a pool of, say, for instance, M aggregation rules. And at each iteration, after receiving the updates, it draws one of those aggregation rules uniformly at random. And this way, it prevents the adversary from being omniscient. And basically, the adversary cannot control the optimization trajectory. This method is called MixTailor, and it successfully defends when well-known robust statistic methods fail. It turns out that MixTailor achieves 2% of an omniscient aggregation accuracy on MNIST. An omniscient aggregator is a hypothetical one that knows exactly which updates are faulty or based on attack. Okay, in terms of theory, if T sub I denotes the number of elementary operations for an informed adversary to design a tailored attack for a given aggregation rule I, if we use this simple randomization method, we make the problem harder for the adversary. So the attack complexity will monotonically increase by M, because the attacker does not know which attack will be effective against a random aggregation rule at the server side. So, for instance, each of those aggregation rules they have their own vulnerabilities, but there is no single attack that is effective for all aggregation rules. So the attacker can potentially select one of those attacks uniformly at random, but it's not effective. It can choose one attack strategy, again, is not effective. So the main point is like the complexity of designing a tailored attack will be much higher when we increase the number of aggregation rules at the server side. And we can also show that when the number of honest clients sufficiently large, then we can establish almost sure convergence for both IID and non-IID settings and non-convex problems. Here we show some experiments. This omniscient scheme provides an upper bound. It's, let's say, it's a ground truth, a scheme that knows exactly which updates are from the attack. So this is not something that we can achieve. We want to get as closer to the omniscient scheme. And we compare MixTailor with two robust statistic-based methods. And it turns out that those basic methods are very easy to attack, but MixTailor defends consistently when other methods fail, and it has much less fluctuations. Finally, this is an ongoing work, but I would like to talk a little bit about this. So this is about robustness to natural distribution shifts. So distribution shifts is a well-known problem in machine learning, deep learning for several decades. Here, the issue is that we have a trained distribution, but we have a different test distribution. For instance, in medical diagnosis problem, the distribution of diseases vary across potentially collaborating hospital, and even for one single hospital changes over time, for instance, due to pandemic. So our goal is to find a model that is the best for the overall test error of these clients at the test time. So we want to focus on generalization error instead of empirical risk or training error. And how we can achieve so, we use some importance weighted empirical risk methods. So basically, instead of classical empirical risk minimization, we estimate some density ratios and we find which training samples are the most important one for the test error. And when we want to train, if we identify those training samples and we focus on them and we give high priority to them, then we achieve a model that basically minimizes the overall test error or overall generalization for all these clients. All right. So as take-home messages, deep learning is characterized by massive data sets, large-scale deep models, stochastic gradient descent, and multi-GPU or multi-client settings. But we need to handle significant challenges such as scalability, robustness, also some other challenges that I didn't discuss, like privacy, fairness, interpretability. So some methods can be helpful to improve these challenges, such as compression improves scalability, and this randomization is a principal way to improve security in large-scale deep learning.